We're going to use Stokes Theorem to evaluate the line integral over c of f dot dr. Our vector field is f of x, y, z is equal to I plus the quantity of x plus y, z, j plus the quantity of x, y minus the square root of z, k. We're told in the instructions that the boundary curve c is oriented counterclockwise when viewed from above. As for c itself, it's the boundary of the part of the plane 3x plus 2y plus z is equal to 1 in the first octant. Now, even though we're evaluating the line integral over c of f dot dr, we're again told to use Stokes' theorem. What that means is that we're actually going to find the surface integral of the curl of f dot ds. And remember, the surface integral is a double integral. Well, clearly we need some things, right? We need the curl of f. We need ds. Let's start with the curl of f. You should verify that our curl of f is x minus y, comma negative y, comma 1. As for ds, remember ds is equal to, in this case, I think we can say rx cross ry times dA. We can express z in terms of x and y and find their partial derivatives, or we can note that because we have a plane, its normal vector is going to be 3, 2, 1. Because the coefficients in the equation of the plane are 3 in front of x, 2 in front of y, and 1 in front of z. Don't forget the dA. Oh my gosh. Now let's see how our surface is going to give us our limits of integration. Looking at the equation of the plane, we can see that the x-intercept would be 1/3, 0, 0. The y-intercept would be 0, 1/2, 0. And the z-intercept would be 0, 0, 1. Connecting those gives us the portion of the plane that lies above the first octant. And we can see that our normal vector here is 3, 2, 1. I mean, we can't see it in the picture, but you can see that a positive x, positive y, and positive z components will all create a vector that points out into the first octant. And we can see that we have a region in the xy plane, D, and that'll help a lot because our dA needs to be in 2 dimensions. Remember, we were told that the orientation of C is counterclockwise as viewed from above, and so the positively oriented curve C, that's how this works out to be, agrees with a normal vector that points roughly up, because if your head is up and you're walking around the boundary curve, then the region D is on your left. As for D in the xy plane, if z is equal to 0, then we get 3x plus 2y is equal to 1. So I'll let y go from 0 to 1/2 of the quantity of 1 minus 3x, and x will then go from 0 to 1/3. Putting that together as an integral, we're going to say here that the double integral over s of the curl of f dot ds is equal to the integral from 0 to 1/3 of the integral from 0 to, what did we say? 1/2 of 1 minus 3x. And then we find the dot product. X minus y times 3 is going to give us 3x minus 3y. Negative y times 2 is going to give us negative 2y. And 1 times 1 is going to give us plus 1. We set this up in the order dy dx. Simplifying the integrand, we get that this is the integral from 0 to 1/3 of the integral from 0 to 1/2 times 1 minus 3x. Our integrand is then 3x minus 5y plus 1 dy dx. I will leave the details to you. You should confirm that we get the answer of 1/24.